once more to our lectures based on application of finite difference method to scalar transport problems. This is our module outline, and we had been working on the last topic, that is applications of finite difference method to scalar transport problems. In the previous lecture we discussed application of finite difference to one dimensional heat conduction, which was based on what we call node or vertex centered finite difference formula. We introduced a cell centered grid for finite difference discretization, and we looked at how do we modify the boundary conditions. The boundary conditions have to be taken care of by what we call ghost cell. We have to incorporate ghost cells and ghost nodes to incorporate boundary conditions. We did one part, that is the incorporation of Dirichlet boundary conditions, and in this lecture this is where we are going to continue from. So this is our second lecture in applications domain, overall lecture 8 on finite difference, application of FDM to scalar transport problems, part 2. So we will continue with our cell centered grid for finite difference discretization from where we left in the previous lecture, and then we would have a look at application of finite difference method to two dimensional heat conduction, then transient heat conduction and advection diffusion problem. If time permits, we will take up the computer implementation aspect in this lecture. So now let us get back to what we were doing in last class. We wanted to solve using finite difference this one dimensional heat conduction problem with heat generation. So governing equation for K del to T over del x square plus Qg is equal to 0. At the left edge of the slab, that is at x is equal to 0, we had temperature specified, and we saw in what way we can incorporate this temperature specified our Dirichlet boundary condition. At the right edge of the slab, that is at x is equal to L, we have got a convective boundary condition, that is minus k dt by dx at x is equal to L is equal to h into T minus Ta. So now we need to find out how do we take care of this derivative boundary condition, and in what way does it change our discrete equations. So once again we would continue with the cell centered uniform grid, and of course now in this case all our grid points are, or the nodes, they are internal. So we would as usual use 3-point CDS scheme for finite difference approximation, and we have to modify only this nodes or the equations for the nodes which are close to the boundary. So we have already seen one part, and we would again try to use central difference for incorporation of the boundary conditions which involves derivative at the right boundary. So let us see how do we incorporate the derivative boundary condition. Okay. Cell centered finite difference scheme. So let us draw our grid. Our nodes are located at the centroids of each of these cells. Node 1, 2, 3 and so on, n minus 1, node n. This is our right boundary where we have our convective boundary condition specified, and we had as left boundary T is equal to T bar. Here we have minus k del T bar del x is equal to h into T minus Ta. So as I mentioned earlier, since all these grid points happen to be internal, so at each grid point we would replace our governing equation by a discrete counterpart using central difference approximation. So, for any internal grid point, in fact please note that now all our grid points are internal to the problem domain, it is I is equal to 1 to n using series discrete equation takes the form AW T I minus 1 plus AP T I or TP, but for the time being we are going to prefer using that I index AE T of I plus 1, and this we said we are going to write it QP I. So, this is the same as what we had done earlier with the vortex best scheme, absolutely no difference. Our A, the way we rearrange the terms, our AP was equal to 2, AE is equal to AW is equal to minus 1. Now, the values of these coefficients would change for values of AP, AE and AW would change for nodes 1 and n which are close to boundaries or which are adjacent to boundaries. So, we have already seen one change, that is we have seen the effect of Dirichlet boundary condition at node 1. There was Dirichlet boundary condition specified at left hand, and how does it affect these coefficients for node 1 that we saw earlier. So, now we will take case 2, that is the incorporation of convective BC at x is equal to L. So, once again we would introduce our ghost node. So, this is our actual boundary, this put the internal parts as shaded. Okay. This is our internal shell whose middle point is our computational node with an index n. Now, let us introduce a ghost cell which is outside of it, and the centroid of this ghost cell, let us put this by dotted line, let us call or give it an index n plus 1. Now, with this arrangement our boundary point that happens to be the midpoint between these nodes, actual node n and the external ghost node. So, this is our so called ghost node. So, boundary point is midway, this is our boundary, x is equal to L is midway between nodes n and n plus 1. So, that tells us that we can now use our second order accurate central difference scheme. So, let us use second order accurate series for discretization of derivative dt by dx. So, what do we get? dt by dx at x is equal to L. This we can approximate as t of n plus 1 minus Tn divided by delta x, because the distance between nodes n and n plus 1 would be the same as our normal grid spacing delta x. Now, let us have a look at our boundary condition. So, BC was minus k dt by dx at x is equal to L. This was equal to h times t minus Ta. So, on the right hand side we have got a nth term, that is our t sitting here. So, this t is at x is equal to L. So, we need to approximate this TL as well. So, let us use simple average. So, use simple average to approximate TL, that is our TL becomes half of t of n plus 1 plus Tn. So, now next we substitute or we use these equations 2, 3 and 4. So, from equations 2, 3 and 4, what we will get? On the left hand side we have minus k, and approximation for dt by dx would be given by t of n plus 1 minus Tn divided by delta x. On the right hand side we have got h times 1 by 2 t of n plus 1 plus Tn minus Ta. Let us try to simplify this expression. Our main purpose is to eliminate. So, what we are looking for, our objective is to obtain an expression for Tn plus 1, because Tn plus 1 this is just an intermediate variable which we have introduced for our formulation. It has got no other purpose to serve. Okay, so we can write our left hand side as t of n plus 1 minus Tn. Remaining terms let us transfer to the right hand side. So, we get minus h delta x divided by k, and inside we have got 1 by 2 Tn plus 1 plus Tn minus Ta. Let us transfer the remaining term in Tn plus 1 to the left hand side and bring Tn to the right hand side. So, we get t of n plus 1 within brackets 1 plus h delta x by 2k. We have just transferred the first term here, half Tn plus 1 multiplied by minus h delta x by k to the left hand side. So is equal to Tn times within brackets 1 minus h delta x divided by 2k plus h delta x divided by k times Ta. So now this gives us an expression for this intermediate quantity Tn plus 1, which we have introduced as 1 minus h delta x divided by 2k, the numerator, divided by 1 plus h delta x by k multiplied by Tn plus h delta x by k divided by 1 plus h delta x divided by 2k whole thing multiplied by Ta. So now this expression for Tn plus 1, it essentially contains our boundary condition. So this contains the effect of convective boundary condition. So now let us go to the discrete equation for, consider the discrete equation, or rather discretized equation obtained using series for node n so this is A W T of n minus 1 plus AP times T of n plus AE times T of n plus 1 is equal to QP at n. So all that we need to do is, now we need to eliminate Tn plus 1 from here using equation 5. So eliminate Tn plus 1 using equation 5, and this will give us AW times T of n minus 1 plus, let me write or introduce a new term, AP prime Tn is equal to QPn prime. So this becomes our modified equation for node n. Node n, where our AP prime would be our original AP plus AE times 1 minus h delta x divided by 2k divided by 1 plus h delta x by k, sorry, this should be 2 k's everywhere. And similarly, our QP n prime is the original value of QPn plus the additional term which comes from the effect of convective boundary condition. So, it would be minus AE times, okay, now we are transferring the contribution to the right hand side, h delta x by k divided by 1 plus h delta x divided by 2k times TA. So, what we can say is with self-centered finite differences, the life became a bit difficult. The implementation of boundary condition that required some effort, but does this effort translate into any gain in computational efficiency or numerical accuracy? So, this is what the questions we need to ask ourselves. So, question is, implementation of PCs is more complex than usual node based FDM. So, what are advantages, if any? Because we have spent some good amount of effort on the implementation of these boundary conditions, so it will complicate our coding effort as well. We will require a few more computations. So, what is the gain? One thing which you can guess, we have used, so note here, we have used second order approximations for all derivatives. Okay, we use central difference scheme for the discretization of d2t by del x squared term in our governing equation, and we also used a central difference approximation for evaluation of dt by dx term in the boundary condition. So, what we said, yes, first thing is the perceived advantages, hopefully we should get more accurate numerical solution. Is there any other benefit? For that, let us have a closer look at the complete system when we assemble. So, let us write our just system matrix. So, our system matrix with cell centered scheme If you remember for the case 1, what we had, there was change only in the diagonal term, that is AP, AW dropped out. So the first row we are left with 2 terms, that is AP1, let us call it, we use a symbol prime, or rather to make it clear, let us call it APM, that is modified coefficient m at node 1, and then usual value of AE. Now this AE would be the same for remaining terms. In the next row we get AW, then usual value of AP and AE. So this is our system matrix A, and so on. We can keep writing it. We get only the 3 diagonal terms, rest of the terms would be 0. Okay. Now let us come to the last row, which corresponds to node n. So what we found from the previous equation which we had derived, there was change only in AP. AE will not exist, this is the last diagonal. So we will get APN double prime. So this is a modified term, AW remains same, and note that the way we have written our AE and AW, they are both equal and their value was -1. So what you can see from this matrix, now this matrix is, see, matrix A obtained from cell centered finite difference discretization is symmetric. So this is a stark contrast with our previous formulation, where our nodes were aligned with the boundary. The first node was on the left boundary, the last node, that is n plus 1th node, was on the right boundary. There we saw that system matrix is not symmetric, but here we have got a symmetric system matrix which has got scores of advantages in numerical solution. Okay. So we have got tremendous advantages in numerical solution, because we have got specialized schemes for symmetric systems using specialized schemes for symmetric systems. For instance, if you want to use an iterative scheme, we have got a very beautiful iterative scheme which is applicable, that is our conjugate gradient method, which is a very simple and yet very powerful iterative scheme, a very efficient and simple to program iterative scheme. And of course, this advantage, or like this observation, is pertinent for the case of multi-dimensional problems. For 1D problem where we have got only a tridiagonal structure, we are happy with TDMA. TDMA does not care whether a matrix is symmetric or unsymmetric. So, this advantage is basically it is of main interest for multidimensional problems. Though we derived or we showed this matrix to be symmetric only starting with a 1D problem, but exactly same structure we would obtain if we had a 2D or 3D problem. If you want, you can verify it yourself, and the procedure for implementation of boundary conditions would remain exactly the same which we have discussed for our simple 1D case. I would like to leave certain things as an exercise for you. I just mentioned this matrix is symmetric. Can you open or check with your linear algebra book what are other mathematical properties of matrix A which will help in choice of numerical schemes for solution of our A phi is equal to Q, this system which we had. We want to solve it numerically. So, are there any other properties which would be very helpful? In particular, find out if A is positive definite. Okay, I will just close this self-centered approximations with a remark that this scheme we use exclusively in the solution of Navier-Stokes equations. So, we will have what we call a pressure Poisson equation, it is an elliptic equation, and for the solution of pressure Poisson equation we will choose pressure nodes to be at the centers of our cells, and the resulting system matrix would be definitely symmetric, and that will help us in the solution for pressure Poisson equation. Now, let us have a look at a 2-dimensional heat conduction problem and see what sort of discretization we can do for this. So, let us consider for the sake of simplicity a steady state heat conduction in a 2-dimensional domain without heat source or sink. If the heat source or sink is present, that can be taken care of very easily the way we have seen with 1-dimensional problem. So, this particular problem where there are no source or sinks is governed by our Laplace equation, that is del 2t by del x square plus del 2t divided by del y square is equal to 0. So, we have got second order derivatives, and we have already learned multidimensional formulae for second order derivatives. So, what do we do? For finite difference discretization, we will consider a uniform grid of the size delta x in x direction and delta y in y direction. And let us adopt a 5-point series molecule for finite difference approximation at the internal grid point. So, if you do that, what happens? Now, let us draw our computational molecule to clarify the things a bit more. So, 2-dimensional heat conduction, and what we are doing, the way we are proceeding now, that can be easily extended to 3-dimensional problems. So, 5-point series molecule, we are just dealing with the stencil. So, these nodes could be at the cell centers or these could be at the edges, we do not really need to worry about it. So, our node P ij is eastern neighbor E I plus 1 comma j, western neighbor W I minus 1 comma j, is northern neighbor in y direction, that will be I j plus 1, and the indices for southern neighbor would be given as I j minus 1. So, at point P, that is at point given by the indices I and j, our del 2 t by del x square. Remember what we said, if you want to write or want to find out the approximation formulae for multidimensional derivative, look at the variable with respect to which we want to differentiate. So, here it is x, so x means only I indices will change in our formulae which we had derived for one dimensional problems. Suppose here we are using series S. So, we will use a central difference scheme, P is our central node, values at W and E and P, those are the ones which would be involved in approximation of the derivative del 2 t over del x squared. So, it is simply given as t I plus 1 j, that is the value at the eastern neighbor, plus t I minus 1 comma j, the value at the western neighbor, minus 2 t I j divided by delta x squared. So, this is the approximation for the first second order derivative in our governing equation. Similarly, the second derivative which we had del 2 t by del y square at the grid point I comma j, would again use a series approximation. So, now the values at grid point P, N and S, those will be involved because now we have to differentiate with respect to y. So, I indices will be kept same in our numerator terms, only j indices will change. So, t I comma j plus 1 plus t I comma j minus 1 minus 2 t I j divided by delta y square. Then what would be the discrete equation at the node P? So, discretized equation, substitute the approximation of these derivatives in a governing equation. So, we get discretized equation at internal node P, and this would be given by t I plus 1 comma j plus t I minus 1 comma j minus 2 t I j this multiplied by delta x square to simplify the things a bit. So, we get a ratio of delta x square by delta y square into t of I j plus 1 plus t of I j minus 1 minus 2 t I j is equal to 0. We can introduce a shorthand notation. So, let's use a symbol alpha, or rather let us use beta. Beta is equal to delta x divided by delta y So we can write the preceding equation in bit more compact form as t of I minus 1 comma j plus t I j within brackets 2 plus 2 beta squared minus t of I minus 1 comma j minus beta square times t of I j plus 1 minus beta square t of I j minus 1 is equal to 0. So, this can be easily recast in our generic form, that is A w t w plus A p t p plus A e t e plus A n t n plus A s t s is equal to q p. We can easily compare the coefficients and write these values here. That A w is equal to A e is equal to minus 1, our A p is equal to 2 times 1 plus beta square, and A n is equal to A s equal to minus beta square. Handling of boundary conditions is exactly the same as we had done previously in the case of one dimensional problems. So, nodes at boundaries handled exactly in the same way, as we did for 1D problem, to incorporate boundary conditions. And once we have incorporated the boundary conditions, we can easily obtain discrete system of equation by assembling the things at all the nodes, and you can observe for yourself that we will get a pentadiagonal system. Okay, so this is what we had, our generic discrete form for 2-dimensional heat conduction problem. So, implementation of BC, that will depend on our choice of grid, that is to say whether we have taken a vertex centered computational node or a cell centered computational node. So, if you have got usual node based, that is vertex based schemes, we have to use one sided difference formula BDS or FDS as appropriate for derivative boundary conditions at any boundary. Dirichlet boundary conditions are taken care of without any problem. For cell centered scheme, we will proceed exactly the way we did in 1D, that is we will introduce the concept of ghost cell, and we will use simple average for Dirichlet BCs. That is how we will incorporate and eliminate the values corresponding to the ghost cell, and thereby include the specified boundary condition in the discrete equation for the node close to Dirichlet BC. Similarly, we can use central difference scheme, which involves value of the variable at the ghost cell use your boundary condition to obtain that expression for that variable at the host cell, substitute that in this discrete equation for the node adjacent to this derivative boundary, and we are done with introduction of boundary conditions. Next, suppose we had instead of steady, our problem were transient one. So say for example a transient heat conduction problem in a 2-dimensional domain with constant diffusivity. The case of variable diffusivity can be taken care of, algebra would become a bit more involved, but as far as finite difference approximation is concerned, the steps would be fairly similar. So now let us take the case of constant diffusivity. So del capital T by del T, very small t is a time variable, is equal to alpha times del 2t by del x square plus del 2t by del y square. If we had a 3-dimensional problem, we will have one more term del 2t by del z square, and here our alpha denotes thermal diffusivity. So for finite difference discretization, okay, let us consider uniform grid of grid size delta x and delta y, 5-point series scheme for finite difference approximation at internal grid points. This is what we have already seen earlier for 2D case. 2D steady case we derived this as a central difference approximation. What happens on the left hand side? Now del as a partial derivative of capital T with respect to time, now that becomes an ordinary derivative. So that is why I have used symbol d, dt by d small t I comma j at grid point ij is equal to alpha times this bracketed terms t I plus 1 j plus t I minus 1 j minus 2 t I j divided by delta x square plus t I comma j plus 1 plus t I comma j minus 1 minus 2 t I j divided by delta y square. So in generic discrete form we introduce our symbols AP, AE and so on, so you can write by introducing a new symbol CP. For the time being, of course, was the way we have written it, Cp was equal to 1. So Cp dt by d capital T by dt at point P is plus APTP plus AETE plus AWTW plus ANTN plus ASTS is equal to QP. This QP might be present in case if we had some Stokes terms coming from somewhere. Okay. Now if you collect such discrete equations at all nodes, so in this case we will get an ordinary differential equation in time. So all these C's coefficients, they will be combined in this matrix C. So this capital C matrix is basically a diagonal matrix. So capital C times d capital T by dt plus capital K into T is equal to B. Now these bold symbols, bold capital T indicates, or it is a vector of the temperature values at all the grid points, and capital B denotes what we call the load vector. So in finite difference, finite volume or finite element terminology, specifically in the case of finite elements, this matrix C is also referred to as what we call a capacitance matrix, matrix K is called a stiffness matrix, and B is called the load vector. So same term is also borrowed and used very often in finite difference and finite volume literature for transient heat conduction problems. So this is a simple system of ordinary differential equations. One, it contains only first derivative, and this has to be solved using a time integration scheme which we will learn in a later module. So until then, let us wait and learn few more techniques of finite difference discretization for convective transport problem, which we will do in the next lecture, and we will discuss some computer implementation aspect also in the next lecture, and then we will take one by one. The first we will consider in the next module the solution of algebraic equations, and then in the module after that we will take up the case of the solution of these ODEs or ordinary differential equations in time.